m is the coefficient of dx, n is the coefficient of dy, and p the coefficient of dz. So our f function is this, so that this integral with this curve give us all of this. The curve is this ellipse, so we take the surface to be the interior of this ellipse, the plane interior of the ellipse with this normal vector. Our function f comes right out of the integral, so that we can find the curl of f, and that's very easily done. We simply write the determinant, take the derivatives, and I believe the curl of f for this region is negative 2i minus 2j plus k. Error alert, I don't know that there is one here, but be careful. You know, partial with respect to y of y is 1, partial with respect to z is 3, 1 minus 3 is negative 2, and so forth. Putting all this together, we see that curl f dot n equals what? Negative 2i dotted with 2z, which is going to be negative 4z. Negative 2j dotted with 3x, which is negative 6x. K dotted with yk, which is just plus y. So this is the curl of f dot n, the quantity that we're going to integrate over this surface. And again, what's the surface? The surface is given by these inequalities. And back up a minute. I just dotted the curl of f with f, not with n. Okay, curl of f dotted with n is negative 2i dotted with I over the square root of 2, which is going to be negative square root of 2 over 2, and k dotted with k over the square root of 2, which is just square root of 2 over 2. And I'm not sure I said that right, but we can see, and you can verify, that curl of f dotted with n equals negative 2i minus 2j plus k dotted with I plus k over the square root of 2, which equals negative 2 over the square root of 2 plus 1 over the square root of 2, which is negative 2 times the square root of 2 over 2 plus the square root of 2 over 2, which is 3 times the square root of 2 over 2. Curl of f dot n is integrated over this surface, so that the integral of curl of f dot n over our surface is going to be the integral first from negative 1 to 1 with respect to x, and negative square root of 1 minus x squared to the square root of 1 minus x squared with respect to y integral being first, and our ds, our area interval. Remember that ds is delta y, dy dx over n dot k, our area increment from the plane divided by the cosine of the angle between the surface and the k vector. And that's going to be just square root of 2 over 2. We'll calculate that in just a second. And what we're integrating is just the curl of f dot n, which is 3 times the square root of 2 over 2. So we have the integral from negative 1 to 1 of the integral from negative square root of 1 minus x squared to the square root of 1 minus x squared of dy dx. N dot k is just 1 over the square root of 2 over 2. So that what we're going to have is we're going to have dy dx, and 1 over the square root of 2 has reciprocal square root of 2, and that can't be right. never mind, that's right. Okay, square root of 2, meaning that any portion of this ellipse that's at a 45-degree angle with the xy plane projected down into the xy plane becomes 1 over the square root of 2 times as great. Square root of 2 being the cosine or the sine of 45 degrees. You can put that together and make sense of that. In any case, then we have 3 square root of 2 over 2 multiplied by that square root of 2. So we have the integral of square root of 2 times 2 is 2, so this just becomes 3. We have, not sure I have started writing a negative sign, but let's make that into a 3, really ugly 3, times the integral from minus 1 to 1 of the integral from negative square root of 1 minus x squared to the square root of 1 minus x squared dy dx. This is nothing but the area of the unit circle. So without even going to the trouble of doing the integral, we know that this integral is going to be pi. And if we've done everything correctly, then we've established that this original integral equals 3 pi. Now, it wouldn't have been difficult to plug in our parameterizations here, knowing how the curve is parameterized, and do this integral. Matter of fact, probably would have been easier than what we did, but we're just illustrating the fact that we can evaluate an integral around a curve by evaluating the surface integral of the curl of f dot n. And sometimes this is an advantage. Sometimes we know by symmetry of the surface and the function that this integral is, for example, 0, which makes it a lot easier to evaluate this.